Hello, my name is Victor, and in this video I'm going to show you how to create this wall inspired by Rudy Ricciotti's building in Revit with the help of Dynamo. So as last time, I'm going to talk about Rudy Ricciotti again. And I briefly mentioned in the previous video about this building of his, La Bibliothèque Multimédia à Vocation Régionale, pardon my French. And I'm still not sure if this was built or not, but what we can see here are these distinct walls. And these walls have the shape of a Voronoi diagram. And I mentioned that it's probably not built because the wall is entirely different. So this has to be cast in place. It couldn't be like a panel, unlike the last one. So what's a Voronoi diagram? You can Google it, of course, and you can find a lot more information about it than I have time to explain now. But to briefly scratch on the surface of it, this here is an example from Wikipedia for a Voronoi diagram. The simplest explanation is that we have a field, in this case this square, and we have these seeds, these points called seeds. This is where we start from. And for each of these seeds, we have a field inside that one, which is defined as all the points around that seed point that are closer to this seed point than to any other, which means that at each edge, these imaginary points on this edge, on this line, are at equal distances between these two, and on this line there are at equal distances between these two. So without spending more time on this, you can definitely check that for yourself. Let's go to Revit and Dynamo. So what I have here for a start is just my wall. It's a surface by loft that I'm going to use to represent my wall. And Dynamo has its own Voronoi node. Here you can see that there is a 2D Voronoi by points in the Springs nodes package, but I'm going to use the by parameters on surface. This is the out-of-the-box Dynamo node to create Voronoi diagrams. How does it work? It needs a face first, and then it needs UVS parameters. And these UV parameter, as here is for multiple, are just like coordinates. On each surface, we have a U direction, a Y direction, and these can be depending on, so imagine in this case, since this is a wall, this is going to be like a horizontal and vertical direction, but this surface could be anything. And these parameters are normalized, which means that the base point is always 0 and the maximum point is always 1. So we have values between 0 and 1. And the quickest way to do this is to use some random points on this surface, random UVs. So we need UVs, so we type in here UV dot, and we can see here by coordinates. And we need to push in a bunch of values for these coordinates. These values, numbers between 0 and 1. And conveniently, we have this random list in the math library, which is giving us exactly that. If I type in 10 here, it's going to give me 10 numbers between 0 and 1, and I'm going to switch this to automatic for the moment. So we can see we have 10 values from 0 to 1. So we link that here. And let's make another random list, but again with the same amount. We need the same amount because we are talking about coordinates. So we need to have U and V coordinate for each location, for each UV. And now we have 10 UVs here, and when we connect it here, we get these weird lines in the preview. Because to make it look more like Voronoi, we'll need more like 50 of those seed points. So I'm just typing in 50 here. And if we are going to make this parametric, we can always use a slider. And I'm going to go for the integer slider. Set it to 50 here, so I can easily change it later. And I'm shift clicking here to move these connectors to the other one. Okay, so here we have this Voronoi, and these are now stretching to somewhere far in the distance. Okay, so far so good. Don't need that yet. And what's our next step? Our next step is to actually make these cells, like if we go to, because so we are now here, we have these fields around these points that we don't see, but we want to make the actual cells to an actual wall. And we have a few options to do this. Of course, first thing we need to do is to actually make the cells. And to do so, I'm going to need to extract each individual surface from these. And I cannot simply slice our surface with these curves, unfortunately. So what I need to do is I need to extrude these curves first. So extrude. And when I select the distance method, this is going to extrude each curve in its normal direction, which in this case is going to be perpendicular to the surface. It's going to be perpendicular because these curves are drawn on the surface. So I'm not concerned with the distance. The distance of 1 is enough for what I'm going to do. And now here we're going to have a list of surfaces for each individual curve. And we're going to combine them with surface by joint surfaces, like this. Stick it here. And now all these individual surfaces are going to become just one single entity. One polysurface. And now I can actually cut that surface with that one. How to do this? Geometry.split, like this. So I connect my geometry here and the polysurface here, and I run this. And you can see that we have a few things on top of each other. We have 47 surfaces now. I don't want to see the preview of all that, so I'm just going to go select it and hide all geometry preview here. And you can see that these surfaces add up to cover the entire initial surface. And I'm going to take their perimeter curves. So when I type in here perimeter, the second node is surface dot perimeter curves. So now we can see the outlines of each of these surfaces. Okay, now these outlines are individual curves, but I want to offset them in. And to offset them, I have to make them, I have to combine them into a polycurve. So I'm going to type in polycurve by joint curves, like this. And that's all. I now have 47 polycurves. And I'm going to turn off the preview of all of that as well. And then I'm going to use the offset. So this offset here. And I'm going to use a negative value. I'm actually going to connect the number slider here. And for the number slider, the maximum is going to be 0. The minimum is going to be, let's say, minus 300. And then I'm going to make a step of 10. And these numbers I'm just typing in because I'm working in millimeters. So let's see what's a good distance now. You can see that we got an error because some of these cells are too small for this size. So at minus 50 it might work better. Yes, it does. And I don't want to see these curves either, so I'm going to turn off the preview. And you can see now we have all these curves like that. And what we can add here is we can take the perimeter curves of the original surface, which is gonna look like this. You see them, the outline, because this is the shape in Ricciotti's walls. The cells from the Voronoi are the openings of this wall. And actually, I'm going to copy these three actually, copy, paste, and I'm going to connect this here. But for this one, I would need a positive offset value. So I'm going to offset it with, let's say, 200 millimeters to get that outer frame. And now I'm just gonna hide this preview here because I no longer need it. And you can see what we got here. Okay, so far so good. We created our Voronoi shape, but we need to put it inside Revit as a wall preferably, and preferably as a proper wall with all its layers inside. Now there are a few ways to import geometry from Dynamo to Revit, and I'm explaining those in details in my Dynamo course on Udemy, which I'm going to give you a discount code for in the description of this video. And a few ways. So what we are going to do here, since we want to get that proper wall, I'm going to show you first a method that you can use on your own with just the out-of-the-box nodes and probably Spring Nodes, which is a package that you want to have anyway. And then I'm going to show you my favorite way of achieving this, but this way is going to require some Python coding. Just very little coding, I promise, but still some people feel uncomfortable with using the Python nodes. Anyway, so what I want to do here now with these curves, I want to turn them into solids. And the easier way to do this is extrude as solid. Here you can see. And the direction, we shouldn't be worried about this, but the distance we need. Actually, we could probably be concerned with the direction as well if we have flipped normals, but let's see. So let's make that a solid with the thickness of 300. I want my wall to be 300, and now it's extruding it to the back. And let's try the other ones. Okay, so as you can see, when we get cases like that one, some of these are extruded in one direction and some of these are extruded in the other direction. And this is a common problem that we are going to deal with. This depends on how these cells were drawn. It kind of follows the rule of the right hand, if you have heard about this, but yeah, no time to go into this. I'm just going to show you one way you could solve this when it happens. And one way is to actually make the solids in a different way. We can go and select extrude the solids with direction and distance. Or we can go patch those curves and thicken the surfaces. But here I'm going to use that node. So curve, distance, and we need a direction. And how are we going to get the direction? I'm going to go and type in normal at parameter, and I'm going to take that node. And I'm going to connect it here to my initial surface that represents my wall. And I'm going to leave this blank because they have default values of 0. So now this is giving me a vector which is perpendicular to that initial surface. And I'm going to use that same vector here for this direction. Okay. And I'm going to use it for the others. So now you can see that all of these are extruded in one direction. But again, actually, I don't want to see all of this. I want to hide it. And I want to use solid difference, which is a Boolean command. We can use difference O to subtract from the big solid all the others. And you can see we have two nodes. We have difference O, which works with multiple inputs here, and with just one input. Okay, so now we have created that geometry as 3D. And as I said, there are a few ways to put that inside Revit. And what you can do with spring nodes, or the equivalent in the out of the box, in spring nodes we have something called family instance.byGeometry. So why do we need that? This is going to create a new family, and it's going to place this instance of this family inside the project. And we can have this family as a mass, so then we can actually use a wall by face on this. And then the out of the box equivalent of this node is family type by geometry. This is from the out of the box, but this is only creating a type, and later we need to place this type additionally inside the project. So that's why I prefer the one from Springs. And before doing that, I'm actually going to switch here to manual. Okay, so this is my geometry. We need a family template path here. So I'm going to select the file path like this. And I need to browse to my family templates. And I need to select the mass template because I want to create a mass. Then I need to name that mass. Wall mass 1, let's say. This is the name of the family. And I need a category. So I need to select one category from the drop-down menu. Like this. And I want to select the mass. So I'm going to connect it here, and now I'm going to hit run. And I switched to manual because when I'm interacting with Revit in such a way that I'm creating new families, I prefer to have full control over it. And now you can see that this was created inside Revit. If you don't see it, you should make sure that this is turned on and that the masses are enabled. And once this is done, we can manually create the wall by face, like this. Or we can actually use a node in Dynamo that creates a wall by face. But in this case, since I'm only dealing with one wall, I don't care too much if it is a manual way or not. And this is pretty close to the character of the walls that we are seeing in Ricciotti's building. Okay, so let's go back here. Now the other way that I mentioned that I prefer is because this now is just wall by face, and I don't like having that unless I totally need to do it. Like if I need a double curved wall, then this is the only way. But now it's just a vertical wall, and we can edit its profile. There is, to my knowledge, no node that is currently doing this. Maybe there is in some of the not so popular packages. So that's why we need to do it with the API in Python. But it's fairly simple. And before doing that, I'm just gonna get rid of these two here. And I'm going to remove all of these that we did. I'm going to also remove the extrude solid. So what I need here is this, the final curves. So I don't need the normal parameter either. I don't need the thickness either. What I do need to prepare these curves is I need to break them down. I need to explode them. And this is done with the explode node. Or alternatively, we can, this is actually not the correct explode. I selected the mesh explode, but I need the geometry explode. And we can actually alternatively do this in the Python node, but I want to keep it simple there. So that's why I'm exploding this with the out-of-the-box node. Then I'm going to join them with the list join, like this. And now we have all of these curves joined when I run this in a list. And what I want to do with this list is flatten it. Now this is going to work for one wall only. But imagine we have like a list of these for each wall that we want to create. So we have many curves here. So this is this might fail in Revit, but here I have my Python code, and these are all default imports that I use, and the actual part that is doing the trick is here. So I'm going to create this new Python node like this, and I'm going to connect this list of curves here. I'm going to edit the node. So the first thing that I'm going to do is paste all of these imports. I don't really need all of them, but I usually, especially when I'm developing something, I just paste a bunch of things in the beginning of the node in case I need them later. And then I need to declare my document. In this case, I'm only going to work with the document that is open. And then what I need to do, I need to declare my inputs. So in this case, I only have one input, which is going to be called curves. So this is how we declare it. This is the input in 0, as you can see here. This is in 0. And then I'm going to create a list of walls, which is going to be empty. This is how we do an empty list in Python. And I'm going to use this list to put all the walls that are created in it. Then I need this transaction manager instance ensuring transaction, because we are working with Revit elements. We need to enclose everything we do in a transaction in order for it to work. And Dynamo has this transaction manager that helps us with transactions. So everything that we do when we are interacting from Python with Revit needs to be enclosed in these. And then I have here 2 loops, and this was done for multiple lists of lists. We actually need only 1 loop here, so it's fairly simple to do. And this is how to do it in Python. I'm just going to write it here from scratch. Okay, now bear with me now. It's a really simple if loop, and it's 2021. I'm pretty sure that even if you haven't studied programming or computer science or anything, you have a clue what's a for loop. So, did I say if loop the first time? Sorry, I meant a for loop. So we go in Python for curve, let's say, and curve now is our variable. Sorry. In curves, this is the list that comes from what we have drawn. We actually need 1 more list here, and this list is going to be a list of Revit curves. So I'm just going to name it Revit curves. And we actually need this list to be a special type of a list that Revit can interact with. So in Python, a simple list is declared like this. But since we need this special type of lists that is interacting with Revit, we need to declare it in a slightly different way. So I'm going to type it like this. Curve. And that's all. So now here I can say, okay, turn this curve into a Revit curve and add it to that list. How do we do this? Well, we just type in Revit curves, add the first one that appears, brackets, and then we type in curve for this curve, dot to Revit type, like this. And this is a conversion method that comes from Revit.geometry conversion here. If we don't have this imported, this will not work. And that is one for loop. And then this could actually be outside of the transaction. I'm actually going to move all of this outside of the transaction because we don't need a transaction to do this. Okay, so now that I have moved this here, because I don't really need this loop to be inside the transaction, I need to create my wall. And how do I know how to create a wall? Well, There are a few places on the internet where we can actually check that. apidocs.co is one of them, or if you prefer Revit, apidocs.com. I can recommend these two. So we type in wall, and we can see here we have a wall class, and underneath it we have members and methods. The methods are also in the members actually, and we need a create. And here you can see that we have a few ways to create walls and a simple description of what each method is doing. So creates a non-rectangular profile wall within the project using the default wall type. That is doing enough for me. And then we have another one here, creates a non-rectangular profile within the project with the specified wall type and normal vector, which is similar to that one, but then we can also specify the wall type and a normal. I'm going to use the first one. So how to actually use it inside Python? Well, we say, okay, our wall is going to be created like this, wall.create, and this works because we have referenced here the Revit API. If we don't have this, this will not work. So wall.create, and then we go and look what we need here. The first item is the document. But if you remember, we just declared the document as this thing here. So this is what we put here. Then we put a comma. Then we looked here, and then we need this special list, the I list of curves, which we created here. It's called Revit curves. We place it here. And last, we need a boolean. So let's check what's the boolean doing. The boolean says if the wall is structural or not. And your choice. We can actually make that import. Here we can control it with a boolean, but I'm simply going to type in false because I don't want it to be a structural wall. And that's all. And then in the output of the node we can actually type in wall. So we end up not using this walls list. I can remove it. And note that this Python node now is only working for a single wall. If we want it to work for multiple lists of curves to create multiple walls, we need to loop all of this in one cycle. Or to put this Python node, this Python script node in a custom node, and then we can use the levels and stuff like that. Again, like this video is becoming really long already. So now we're ready to test this. Let's see what's happening. Okay. Let's run this. And here we have created a wall. Let me minimize Dynamo. And this wall now has an edited profile that we can go and edit manually. And we can change its type. We can even play with the shape handles, make the frame thicker. And one thing that is really cool about this method is that we can actually create a wall containing only the inside parts, and we can switch very easily between the two. So what do I mean here? Well, if I go back to Dynamo, you remember where we took these outer curves. and we join them with the inner ones. Well, we can simply connect the inner ones to this flatten here, and we can run that. You can see that we easily can change between having this as the empty part of the wall and the solid. And again, we can modify these handles a little bit. Not too much though, because we might end up having something impossible. Okay, so far so good. And I think this is long enough for a first video on Voronoi. And I'll have to create more to show you how to actually, you know, this shape here now, we don't have any control over it. It's too random and too unusable. So in the next video, I'm going to show you how to control this Voronoi, how to massage it to achieve what we want. Because this shape, even though it is very similar to what we saw in the Rudy Ricciotti facade, let me run that again. Even though this is very similar to this here, it is also kind of different than most pictures that we get for Voronoi. And the reason is behind the distribution of these random points. So in the next video, I'm going to show you how to make a Voronoi with more control over it. But yeah, so this is all for this video, and this file I'm going to share it in the description as well, so you can use it. And if you want to learn more about Dynamo, if you want to see how I learned how to do these things, consider checking out my course on Udemy. It's a good one. And if you want to know more about curtain walls, facades and things like this, I recently started paneling series on Udemy as well. Currently I only have one course, but yeah, you will find links in the description as well. Thank you for watching this long video, and if you liked it, consider hitting that like button. Yeah, thanks, and see you the next time.